Good afternoon. Welcome to this digital meeting with the finalist authors of Premio Cosmos. This afternoon we are going to meet David Lindley, the author of Quale Universo, published by Giulio Einaudi Editore. David Lindley is online. Thanks, Mr. Lindley, for being here with us.
Thank you.
Mr. Lindley will talk with Roberto Battiston, the member of Scientific Committee of Premio Cosmos. Good afternoon, Prof. Battiston. And I'd like to introduce Premio Cosmos. It's a prize born to support scientific culture and scientific dissemination. One of the two prizes is assigned by students, and the other one by Scientific Committee of Premio Cosmos. The students assigned the prize to Guido Tonelli, and now we're waiting to know the winner book for Scientific Committee. I don't want to take too much time, just 2 minutes to introduce David Lindley and Roberto Battiston. Roberto Battiston is an Italian physicist specialized in the field of fundamental physics and elementary particles, and leading experts in the physics of cosmic rays. He was full professor in physics at University of Perugia. He was elected for a 3-year mandate as president of the National Commission of Astroparticle Physics of the National Institute of Nuclear Physics. He moved to the Department of Physics of the University of Trento, where he holds the chair in experimental physics, and where he contributed in founding the new INFN National Center, devoted to space, physics, and technology in the astroparticle sector. On 2014, following a competitive selection by an international committee, he was appointed the president of the Italian Space Agency for 2014 to 2018. David Lindley is a British theoretical physicist and author. He holds a BA in theoretical physics from Cambridge University and a PhD in astrophysics from the University of Sussex. Then he was a postdoctoral researcher at Cambridge University. He was a research fellow in the theoretical astrophysics group at the Fermi National Accelerator Laboratory. He then served as technical editor and writer with the Central Design Group for the Superconducting Supercollider at the Lawrence Berkeley Laboratory in California. He was an associate editor at Nature, a senior editor of Science, and an associate editor of Science News. Since 2000, he has been a freelance science writer and consultant. Today we are talking about Quale Universo, one of the finalist book of Premio Cosmos. Lindley raises important question about what science should be and how it should be approached. Roberto Battiston and David Lindley can start their conversation about this book. Okay, thank you. To you.
Okay, thank you so much for this introduction. It's a real pleasure, David, to be here today for this conversation.
Yes, thank you for inviting me.
Your book is really amazing, and maybe in addition to the title, it is the subtitle, which is really challenging because it's basically about the fundamental physics which has lost its way. Okay, so this is the key point of your analysis, the role and the methodology of physics and fundamental physics, starting from the Greeks until Galileo, and nowadays more recent evolution But let's go directly to the point. Why do you think fundamental physics nowadays has lost its way?
Well, when I was a researcher, this is back in about the early 1980s, I joined the group at Fermilab, and it was at that period that particle physicists and cosmologists began to get together because they realized they had things to say to each other. So, in terms of trying to figure out what happened shortly after the Big Bang, in the few seconds or fractions of a second, the universe is very hot, it's very dense, all these fundamental particles are stewing about. And so at that time, the cosmologists were more interested in what happened back then. And at the same time, particle physicists began to realize that the early universe was, if you like, a very hot, dense, highly energetic experiment where you could try to figure out with different particle physics theories what would happen when all of these things were going on. So there was a productive period, and that was just about when I started, when particle physicists and cosmologists could get together and realize that they had some important ways to help each other. And so this went on for a while, and I was doing some research in that area, but I became somewhat disillusioned because ultimately it's very difficult to test what happens in the very early universe. You make theories about what happened when the universe was, a microsecond old, and then you have to infer down the line what that would mean for us looking at the universe today at an age of many billions of years. And so there are certainly useful things you could say, but I began to think that there was an excess of theorizing. It was very easy in a way to come up with theories, but it was very difficult to test them. And at the same time, this was when the super collider was being proposed in the United States, which, as you know, ultimately failed. This was going to be an enormous accelerator, 50 something miles across. It was never built. The funding fell apart. But the LHC in Geneva, the Large Hadron Collider, came online, and that, after some years, found the Higgs boson. But the question is then, what next? You can't really build an accelerator bigger than the LHC. I mean, you can make one a little bit bigger, but to explore the kinds of energies that particle physicists were interested in, there's really no experimental means of getting at what the theories predict and testing those predictions. So I began to feel that that kind of physics was facing a crisis, in the sense that you could come up with all these theories about how the forces of the elementary world came together. This was the time of electroweak unification and so on. You could make theories about grand unification when all the forces looked similar. But the question is, how do you test them? Can you test them? And I just began to think that ultimately it was very difficult to do. And I wrote a book at that time, back in early 1990s, after I'd stopped doing physics research. I wrote a book called The End of Physics, in which I raised some questions about what this kind of physics would look like if you couldn't really do the experiments. And over the years, I mean, at the time when I wrote that book, I was just interested in the contemporary scene, if you like, of what physicists were doing and what they would do next. And I was somewhat skeptical that it would be possible to go much further, because people were coming up with all these theories about 11-dimensional universes and strings and all of this stuff, and you had to figure out how can you test those theories by making these long chains of inference from what the theory says to what we can observe now. And then over the years, I wrote some more books. I got interested in the history of science. I tried occasionally to read about the philosophy of science, but usually I found those writers sort of defeated me, but I persisted anyway. And it began to seem to me that that kind of elementary physics, the people doing the string theory nowadays and all the offshoots of string theory, they're really operating in a world which is kind of set apart from conventional physics, if you like. Some of the most exciting things in conventional physics today, I know, quantum computers, nanotechnology, nanomaterial engineering. Those are obviously real things. But then you have these people doing string theory, and its various relatives, and they are pure theorists. And it seems to me they're kind of hoping that if they just work hard enough, they can come up with a theory that will be so beautiful and so complete and so logically coherent that they will say, ah, that must be the right theory. But that's not how science has worked traditionally. So in this book, what I tried to do was go back before we had real science, which to my mind is before Galileo, uh, in the days of the ancient Greeks. They also thought you could figure out the universe, if you like, just by thinking about it, by using a kind of philosophical method to come up with logical, coherent theories and explain why the universe is the way it is. But then we got into what we now think of as science, and I think Galileo is really a pivotal figure here because he understood that you could do experiments and you could combine theory and experiment and test them and make predictions and see how things work. And so Galileo threw aside a lot of the preconceptions of ancient Greek thought and put science on the road to what it became. Um, but in simple terms, what I think now is that the people doing string theory are, in a sense, going back to Plato. They're going back to a sort of pre-scientific method. And in effect, what they're doing is becoming a kind of modern philosophy. It's a very mathematical kind of philosophy, but ultimately, it's an attempt to figure out the universe just by thinking about it, because there's so little you can do in terms of experiment and test in the traditional sense. So, in a nutshell, that's what I'm trying to say in this book.
Yeah, I mean, I think this example of string theory is obviously something which is very debated, and as an experimental physicist, I feel strongly something like you says about how useful it is, this approach, to the extent it's not providing a forecast or prediction for observable things. At the same time, however, in the things what happened from the 90s when you wrote your previous books you mentioned before, and now Higgs, which was a highly debated if it was a mathematical theory or a real particle. We found gravitational waves, which even Einstein said, forget about that, it's too difficult to detect. Meaning the same physics, which has, fundamental physics, which has become so challenging, so difficult to test, has been tested with some ingenious, naive techniques and effort, sometimes decades-long effort, and provide a fundamental step in the right direction. Today, we are even able to see black holes. Could you imagine that 20 years ago? Absolutely impossible. Now, what I'm trying to say that what you are describing in your book, in a certain sense, is a kind of a wave between pure mathematics, theoretical philosophy, and forget about the reality, and more practical approaches, which nevertheless benefited a lot about the rest of the capability of abstract thinking, of rational thinking. And the practical approach, very cleverly, as you mentioned in your book, putting together both the mathematics as well human type of thinking, which make it very successful. In approaches like the string theory, which were unable to explain, which are unable to explain anything which can be observed. But maybe what is preventing us to think that in a due time, indication of a high dimension universe could pop up, maybe surprisingly, in some experiment, and then suddenly this approach, so highly theoretical, would become very interesting? How we can say that this will never happen?
Well, I can't say it will never happen. And you mentioned the detection of gravitational waves. When I was doing my PhD, I was working on a model which had little black holes at the beginning of the universe. And so I was very interested in general relativity. And I think the detection of gravitational waves was just an amazing achievement when you consider the kind of sensitivity and the as you said, the enormous effort that went into it. It was a wonderful thing. And similarly, the detection of the Higgs boson at LHC was the culmination of many years of theorizing. The difference is, or let me say that, I mean, with the Higgs boson, um, its mass was predicted approximately, and so it was known in principle that with the LHC, assuming that it worked correctly, either it would find the Higgs or it wouldn't. And if the LHC had not found the Higgs, that would have been a very upsetting discovery to a lot of particle physicists. But it was within the realm of possibility, at least envisioned possibility, to build an accelerator. And similarly with gravitational waves, the search for gravitational waves, as you know, goes back to, I think, the 1970s originally, with various kinds of experiments. So it was always a very difficult challenge. But at the same time, you could sort of see that maybe it was doable with increasing technological sophistication and sensitivity of detectors and so on and so forth. And I mentioned quantum computers earlier. The fact that quantum computers can be built even on a small scale, again, it's an astonishing thing to somebody who grew up thinking about all these, all these mysterious aspects of the quantum world would never really be exposed directly to experimental vision. And that turned out to be the case, that you can measure these things. So I think, as you say, these are all wonderful discoveries. But when you think about going from, say, the Higgs boson to the scale of grand unification, which is the scale at which you want the strong force and the electroweak force to get together, that's just so many orders of magnitude in energy that I don't know how you bridge that gap. I just saw, I think it was in Science magazine just the other week, there was an article about the LHC, which I believe was about to turn on again. And there were people who were worried that, yes, it found the Higgs boson, but that's it. It's not going to find anything else, because there were hopes that it would find some evidence of supersymmetry, for example, which is an important theoretical concept, which so far has not been verified. And if the LHC doesn't find supersymmetry, well, what do we do next? My point is that, yes, there are certainly things we can do in terms of improving experiments and refining tests and so on. But to go from where we are now to testing the predictions of superstring theory, it's such a leap in terms of experimental capability. I just don't even begin to imagine how you can possibly bridge that gap. As you say, maybe some evidence of higher dimensions will suddenly pop into our world. It could be, but there hasn't been any sign of it so far, and I don't know how unequivocal that evidence would be. I mean, you see some little anomaly somewhere in some particle interaction, and you say, well, this is evidence of extra dimensions. But the chain of reasoning getting from, extra dimensions at some tiny scale and very high energy to something we can measure even at LHC, it's such a long chain of reasoning that it's hard for me to imagine that it could be a definitive test. I mean, of course I could be wrong, but I just think when you look at the way that kind of physics theoretically is proceeding right now, it really has kind of detached itself in a way from the mainstream. And so I just wonder whether it will ever be possible to close the loop, if you like, of experimental theory. So that's the concern.
Yeah, I would not disagree with you about how stretched become today the path between the most advanced theoretical physics and the experimental one. However, I'm experimentalist since the very beginning, and I remember that there is a story going on about the discoveries at new accelerators. Typically, in the golden days, a group of physicists come together. They found some theoretical support to search for the topic A, to get the resources to build the accelerator to study the topic A, build the accelerator, build the instrumentation, the experiment, and unexpected discovery. And this happened several times for parity violation, for the discovery, for the new. Only when accelerator becomes so expensive this capability of exploring by making a biggest measure and finding of the cost dimension and time of our race and our capability of that in the last century. The path of discovery was rarely guided by theory. You have the great exception of Dirac that you also mentioned in your book, but in most cases was surprise after surprise, unexpected surprise again. And this was why this physics was so interesting and fascinating. Today is an issue of resources. It's not because the theoretical physics was unable to guide. It was unable to guide also in the past, in a sense. The really new things were always unexpected. Only that today we cannot, independently from theory, test.
Yeah, well, I partly agree with you. There's certainly a question of resources. I mean, as I mentioned, the superconducting super collider, which was going to be built, didn't happen because Congress in the United States decided it was too expensive. And to be frank, I think the scientists who were working on it didn't make a strong enough case for it. But the thing is, even if the super collider had been built, it would have been, you know, 3 or 4 times bigger than the LHC. I forget exactly how big the LHC is. And it would have gone to higher energy, but it wouldn't have been like orders of magnitude. It wouldn't have been 10,000 times the energy. So it would have explored a little more space, and I'm sure it would have found things. So yes, there's a question of how much money and manpower and so on society as a whole is willing to devote to these things. But there's also fundamentally a question of feasibility. You know, how do you do an experiment that tests theoretical predictions or figures out what's going on at energies of, 10 to the 12 GeV? And there's always been some interest in astrophysics for that reason. Some of the early discoveries in particle physics were from cosmic ray experiments. And cosmic rays are raining down on the Earth all the time, and some of them have enormously high energies. And that, if I remember rightly, that's how the positron was first discovered. It was in a cosmic ray experiment. And similarly, when you look at things like quasars, pulsars, these are very high, these emit at very high energies. We have gamma ray bursters in the sky whose nature is still a little bit uncertain. So there are phenomena in the universe that can test what's going on at these very, very high energies. But the problem there is, first of all, even so, the energies are not unlimited. They're not going up all the way to sort of superstring scales. And second, you can't really control the experiments. So in other words, to understand, for example, what a gamma ray burster is telling you about particle physics, you have to know, first of all, what a gamma ray burster is. And that's hard to do. So you're trying to do two things simultaneously. You're trying to understand the particle physics, but you're also trying to understand the nature of the astrophysical experiment, if you like, that's producing whatever particles it's producing. So it's a doubly difficult task. And again, it's still, even with the best, the best of luck, it's still going to be a little difficult to probe exactly as you would like to probe. So maybe I'm too cynical, which I've been accused of, but I think there's such a gap, as I say, between what we can do and what we can see versus what we can infer from superstring theory, say. And when you look at the discoveries, I mean, yes, back in the 60s and 70s, you would build a new accelerator and turn it on, and all kinds of things would come shooting out, and it was great. But there's been a bit of a drought since then in terms of particle physics discoveries. There was the W and the Z bosons back in 1980 something, I think that was. Then you had the Higgs boson not so long ago. There hasn't been that kind of constant stream of new particles or new interactions coming along. So again, I worry that method of doing physics has sort of come to the end of its natural life in a way. And unless somebody comes up with some more ingenious way of doing particle physics, then I don't see how it can go on a little bit further, obviously. But again, there's a limit just in terms of physical possibility, not in terms of resources so much as just the physical capability to do what you would like to do.
Yeah, let me make, you are the cynical one, let me make the optimistic guy in the room. As you remember, a decade ago, for a moment, people believed to have seen the B mode in the cosmological background. If such B mode of the coupling of gravitational waves with the initial matter field be very close to the beginning, if that would have been confirmed, that would have allowed to start to think about accelerators physics with the Big Bang, basically, okay? So this was not confirmed, and there are several experiments trying to get into this for the time being, or maybe it's much smaller than what we think, but for a moment, people believed that could be the next level of accelerator. Of course, it's an accelerator which is totally out of control, but it's exactly where these super theories are aiming to in describing properties of quantum and gravity and elementary properties of matter and field. I mean, it's just an example, of course, it's not materializing, but I totally agree with you. There is a tremendous stretch. You know, sometimes I make the following example. If we were ants, building the LHC would have been impossible. But if we were a multi-planetary race, maybe building a super sensitive radio telescope would have shown to us the answer to certain of the questions that we are not able to answer. Maybe what we are discussing about is only a tremendous effort which is limited by our physical dimension, by the resources, by how much we can stretch our experiment and how much we can stretch our mind. And indeed, it's true, our mind with mathematics can be stretched much, much farther than anything we can do in practical terms. But in principle, I agree that supersymmetry is a big, big question mark. But in principle, it's maybe not about the mechanism which is coming to end. It's simply the resources which are smashing against the roof. But the mechanism itself, the science which Galileo has invented, he never put a time scale in his way of reading nature. He just said that nature has a language that we have to learn to read. He never said that it is within a lifetime or within a century or within 1,000 years. It's just a methodology. What do you think about that?
Well, I think, yes, I certainly agree with what Galileo said. It's getting into the realm of speculation if you start saying, well, in order to pursue the next level of particle physics or superstring theory, we need to build an interplanetary civilization so we can build radio telescopes that span several solar systems. I mean, that sounds great, but I just wonder whether, again, there's a question of feasibility, and maybe it will take, tens of thousands of years. We're in a way, you could say, just at the beginning of science. We've only been doing science for what, 4 centuries in a serious way. So yes, there's a big future ahead of us. And one thing I would say is I understand that scientists, or indeed other people, you can't stop asking these questions. Asking the question of, how is the world built? What is it made of? What are the things that determine how it proceeds? What are the factors that tell you how the universe came to be? You can't just say those questions are too difficult, we're not going to even try to answer them, because how can you stop curiosity? So it really is a practical thing, and I just think that there may be some new way of thinking that will come up soon. To take an obvious example, with people have been looking for a unification of quantum mechanics and gravity for a long time, and that's still a very dark and mysterious area. And I wonder, just because superstring theory has been going on so long, almost 40 years now. It was like when I was a young postdoc was when the first superstring theory revolution happened. So you've had more or less 40 years of this superstring theory. And again, to take the cynical view, there's been an awful lot of work done and an awful lot of papers published and conference proceedings and whatnot. But if you say how close are we really any closer to understanding quantum gravity than we were 40 years ago? I don't know. I mean, maybe in some small ways. But I can't help thinking we need a new Einstein to come along and say, no, you've been looking at this problem completely wrong. Here's a better way to look at it. And maybe that will open up new avenues of discovery. And I would love to see that. That would be great. But again, you have to think, I mean, you mentioned gravitational waves, and that was a great confirmation of general relativity. And it was 100 years more or less from general relativity to confirming gravitational waves. So a very long achievement. So maybe somebody will come up with a brilliant new idea for unifying quantum mechanics and gravity, and maybe instead of 100 years, maybe it'll take 1,000 years for somebody to figure out an experiment to confirm it. So, but it still speaks to the point that that kind of physics is maybe getting beyond reasonable human expectation. We can't stop asking the questions, but if you get to the point where you just can't figure out how to answer them, then it becomes very discouraging. And I used to think sometimes when I look at all the people going into superstring theory, you probably know of Lee Smolin, who's a theorist in Canada, and he's written some skeptical books about superstring theory, although he still believes there are other methods. I mean, he's one of those people who looks to other kinds of theories for explaining quantum gravity. But he made the point that in a sense, superstring theory attracts the wrong kind of people as researchers, people who are extremely mathematical, who think purely in mathematical terms, and who love playing around with all these complicated equations and mathematical structures. And those are kinds of things that were beyond me, I have to confess, when I was a researcher. But people get fascinated by playing with those models and tweaking them and messing around with them and refining them. But in a sense, the point of them gets lost, which is you're trying to solve a physical problem. So you have people who are spending whole careers refining their understanding of what superstring theory is, adding all kinds of mathematical sophistication to it. But are they actually closer to solving the physical problem that they were supposedly trying to solve in the first place? I don't know. And I used to think sometimes people would just get a little bit bored with this and think, why do I want to spend my whole research career doing something that doesn't really lead anywhere? But I think there are certain kinds of people for whom that in itself is just a fascinating pursuit. But as I say in my book, in a way, it's more akin to philosophy than to science, at least as I understand it. So, there is a question of how exactly these questions are to be pursued and what sort of strategy is needed to answer them. And I'm not sure that science in the conventional sense that we all know and love is, maybe it's just not up to the task, and maybe some other kind of approach is needed. But I don't really know. But I find it hard. I can't see the future, but it looks very foggy.
Yeah, but very interesting observation. In your book, indeed, you touch several times, I would say, a human dimension of science in the following way. There are a few examples where a purely mathematical thinking, which has been driving people in the wrong direction, was then corrected and adjusted again with additional mathematical thinking plus some practical approaches to get in the right track. Examples. Describing the orbit of the planets around the Earth with a lot of circles, why circles were the only perfect, and spheres, the only perfect shapes, was clearly bringing to the wrong solution, but eventually model because tool. Or examples about the music described as ratios between multiple of frequencies, which nevertheless were corrected to get the music we like to hear. Mm-hmm. Which in a sense is probably the better music or the truer music which may have. And we can go on like that. You mentioned very clearly that Galileo had the unique capability of using the mathematics he was able to use, but still playing with the errors and uncertainties in a clever way to reach the goal which his internal logic was pushing towards. Okay, so these characteristics of a human mind, together with the tool of mathematics, which is a very general, very powerful, infinite, flexible, excessively flexible, a powerful tool, is this mixture between enough mathematics and something else which is in our mind. You may also touch an issue of aesthetic and beauty in this discussion. You did in your really the magic is. It's not the fact we can read the universe with mathematics, which is the magic. Is the fact we can put together this mixture of the way we think and the tools which we can use about mathematics to make something sensible or useful.
Yeah, your audio was cutting out a little bit, but I think I know what you're asking. You're right that obviously the way we think has an effect on what we determine about the universe. So, I mean, this is getting into philosophical questions about whether, are we constructing an objective reality, or is the science we construct some reflection of some kind of, preference in our minds? The factor that's always traditionally held science, held the iron to the fire, so to speak, is the fact that you can do experiments. So yes, you can have all kinds of beautiful mathematical dreams about what you think the universe ought to look like. And that's what the Platonic people thought with their circles and spheres and everything, but it must be that way. And Galileo realized, no, it doesn't have to be that way. We need to go out and look at what nature actually does. So there's always been this balance between the human imagination and the constraint of experiment, and being able to look at what we see and say, does this actually work? There's a great quote from Niels Bohr that I came across in the course of writing another book. And this was back, I think, in the 30s, when people were even then starting to think about theories that would unite quantum mechanics and gravity. And I can't remember who it was Pauli or Heisenberg was coming up with some idea that he thought would be a great way forward. And he said, oh, it's such a beautiful idea. And Bohr said to him, I don't know what it means to call a theory beautiful if it is not true. And that's always been the constraint, that you have to say, well, does it actually work? And again, coming back to this point, the worry that I have with superstring theory and all its relatives is it's an arena in which human imagination coupled with mathematics has an enormous free play. It's this great space in which you can explore ideas and come up with different notions and different hypotheses, but you have to be able to bring it back down to earth, so to speak, by saying, well, does it actually work? And that is the piece that's missing, or maybe if not completely missing, at least very, very weak. So there's always been a balance between theory and experiment, but you have to have the experimental part of it. You have to have the empirical side of science. And that empirical part of science in superstring theorizing, I think, is just very weak right now. And I don't know what you can do to make it stronger. So the worry I have is that ultimately people will say, oh, this is just such a beautiful theory, it must be right, which is kind of like the Platonic ideal of how science should work. But the lesson of real science since Galileo is that doesn't really work. You have to ask yourself the hard question: does it actually work? It doesn't matter how beautiful it looks or how elegant it might appear to you. Does it actually work? And again, to repeat the point, that I think is what superstring theory is. That's where it's running into trouble.
Your own experience with mathematics, which has been, you love it, you hate it, you use it. I mean, you're a theoretical physicist, so in principle I should anticipate the answer, but nevertheless I ask you.
Well, I remember at school, like before university, when I was learning calculus, I thought it was the most fantastic thing, because it was introduced to us, I think, in simple terms of, somebody's riding a bike, so there's a certain distance traveled in a certain time, and so you can draw a nice graph, and you say, well, what's the speed of that cyclist at any time? Well, it's the slope of the curve, and that's how you figure out calculus. That the steeper the curve, the faster your bicyclist is going, and so on. And then integral calculus, the area under the curve is the distance your bicyclist has gone. And I thought this was such a cool thing, because it was my first introduction to that kind of higher mathematics, if you like. And I loved it. But what I found was, I think I'm sort of limited in my appreciation of mathematics, in that I never developed a fondness for what you might call pure mathematics. So things like number theory, pure mathematicians get excited, like, the relationship of prime numbers and all these things, and set theory and group theory. And I could understand those things insofar as I could relate them to physical concepts. So I got a little bit of an introduction to group theory because of particle physics that I learned. Some of those principles come into play. But when you get into these very abstract realms of mathematics, I just sort of lose my bearings. Unless there's something I can picture that it relates to, I have a hard time with it. So I think the pure mathematicians are the opposite of that. They don't care about what these concepts represent. They just care about the internal logic of it. Does it make sense? So pure mathematics, in a sense, is an extension just of pure logical thinking. And I was not very good at that. So maybe that colors my opinion of superstring theory. But it does come down to this balance. And Dirac was an example of somebody who was very clearly mathematically oriented, and he came up with this idea of the prediction of antimatter because of really thinking about the mathematics of various equations. One of the people I admire greatly, on the other hand, is Michael Faraday. And in a lot of histories of physics, people will say, oh, Faraday, he was the great experimenter. He did all these experiments in electromagnetics and dynamos and motors and all this kind of stuff. And it was wonderful how he did all this. But the thing is, he did experiments because he was thinking about what he wanted to test. He didn't just go into his laboratory and sort of throw wires and magnets together in some random way to see what happened. So Faraday had theoretical ideas in his head about how electromagnetic influences worked. And he devised experiments to test them. And he was able to do that despite the fact that he really knew next to nothing about mathematics. So I think of Faraday as someone who thought in almost kind of a pictorial sense, I think. He imagined electromagnetic influences going through space. And he said, oh, well, if I move a magnet in this way with a wire next to it, then, the influence should affect the current in the wire and all that kind of stuff. So theorists, to my mind, run a huge range from people who are very much mathematical to people who are much more, hands-on, still have a theoretical mind, but they have a sort of pictorial sense of what this theory does. So, to come back to the point I mentioned about Lee Smolin, it's about whether somebody like Faraday, who might have great ideas to offer today in a theoretical sense, he couldn't even get through the front door of a theoretical physics department today. And you could say even the same about Einstein, perhaps. Like, Einstein was clearly a great physicist, but when it came to figuring out general relativity, he got in touch with his friend Michel Besso to help him understand the mathematics. So there's always been this sort of fruitful interaction between people who are imaginative, if you like, in a physical way, versus people who understand the mathematics. And again, I think with superstring theory, because as far as I can see, it's so difficult to understand the physics of all these things, the purely mathematical part is taking on an ever bigger role, and that influences how the science develops. But again, a lot of this may come down to the fact that I just wasn't, for someone who trained as a theoretical physicist, I wasn't that great at mathematics. So maybe that's my problem.
It's very interesting, your analysis. Another guy which was like that was Tesla. Tesla was also a person which was able to draw, sketch both physical schemes and machineries also. So and technical element in a way which was unparalleled. And in a sense, like to I would like to know wrong mathematics to get the right result. I mean, we have plenty of examples like that. Okay, so I'm fascinated by what you pointed out, that that mathematics should be servant and not of the researcher and the scientist and the physicist to get to the result, and not dominate the imagination and the path by the physicist which is analyzing the issues. And it seems like it's a general property. I mean, there are endless examples of the wrong mathematical calculation leading to the truth and the good result. Eventually, mathematics get refined and everything goes in the right direction. But during the process of discovery, this happened in a number of times.
Yeah, and I think, again, I'm sorry the audio cut out a little bit, but it comes down again to this balance. So there was a book that came out some years ago. I didn't really like it. I got to review it for publication, but it was complaining. In effect, we just mentioned Einstein, that Einstein wasn't a terribly good mathematician, and when you look at the papers he wrote, they were full of what a mathematician would regard as mistakes in a sort of pure sense. But nonetheless, he got it right, and people were able to come along later and clear up any inconsistencies. If you look at the people doing superstring theory, one of the Ed Whitman at Princeton is obviously one of the great superstring theorists, and I've seen articles about him to the effect that not only is he a great physicist, but some of his inventions to do with superstring theory have really had repercussions for mathematics and for pure mathematics. And I couldn't tell you in what sense. This is kind of beyond me. And on the one hand, that's a great thing, you might say. On the other hand, does it mean, though, that Ed Whitman is he a physicist or is he a mathematician? And you can't quite do both. I think the mindset of a mathematician is different from the mindset of a physicist. I don't know that with mathematics you can ever use it as a guide to empirical truth. I mean, certainly it's an essential illumination along the way. But once you start depending on mathematics and mathematical consistency and logic to an almost exclusive extent, I just think you're heading into worrisome territory.
You mentioned that Wigner in 1959 made a seminar about how unreasonably efficient is mathematics in natural sciences. And he's explicitly talking, Wigner himself, about miracles. I mean, about something totally unexplained, okay? Which is your opinion about this very point?
Oh, that's a very difficult question. I mean, it was a fascinating lecture. I'd heard of this lecture, but I actually took the trouble to track it down and read it. And he talks about a lot of these aspects of mathematics that to him almost seem miraculous, in the sense that you're searching for the solution to some physical problem. In his case, it had to do with like symmetries between elementary particles. And it turns out here's this whole mathematical structure that's ready and waiting for you, if you like. And you think, well, how did that happen? Because these mathematicians, they were not even thinking about physics. A similar thing happened with Heisenberg and the discovery of quantum mechanics. He was away on this little island north of Germany and thinking about how to come up with a system of quantum mechanics. And he struggled to come up with some mathematics. And eventually he did, but he didn't really know what he would come up with. And then he went back to talk to Max Born, and Max Born, who was trained more as a mathematician, said, "Oh, that kind of rings a bell. I got to go talk to some of my colleagues." And in a sense, without realizing it, Heisenberg had sort of reinvented matrix arithmetic, matrix calculus. The question is, though, I find it difficult to evaluate this question, because on the one hand, you think, well, physics especially, ought to be logical. It's the science, if you like, of cause and effect in a empirical and measurable way. So here's something that happens, here's something that follows from it, and there's a the magnitudes ought to line up. So the magnitude of the thing happening affects the magnitude of the effect it causes. So you think it's got to be logical, it's got to deal with measurable quantities. So almost by definition, that means mathematics. So in that simplistic sense, you say, well, it's not surprising that mathematics provides the tool to construct physical theories. On the other hand, as Vigna pointed out, it's been surprising how often mathematics has already invented mathematical tools that physicists have only later come to realize would be useful in this or that application. And that is, I mean, it's interesting reading that essay of Vigna. He didn't really have an answer to how this was. He just sort of threw up his shoulders and said, "Well, hey, we should just be thankful. We're very lucky." But on the other hand, there's also whole areas of mathematics that so far haven't had any particular application in physics. So there's what we like to call pure mathematics, and we call it pure mathematics because, as far as we know, it doesn't apply to anything in the real world. So, is it significant that mathematics has structures within it that are useful in physical theory? Well, maybe not so much, because if you think of mathematics as being, the entire universe of logical relationships between measurable quantities, which is a very simplistic way of putting it, well, then of course mathematics has to provide the answers, because that's the very tool you need. But it doesn't mean to say that all of mathematics is going to be useful in physics. And it doesn't say that physics is going to use every single tool that mathematics provides. So whether it's a surprise or not that physicists have from time to time found bits of pre-existing mathematics that were useful to them, I honestly don't know. I can't decide whether it's an interesting question or just well, of course, I can't make up my mind on that.
Yeah, in a sense, I would say that if we are here talking together about the universe, ourselves or the people which were before us, it is because things are stable, and if they are stable, there must be laws. And it's difficult for me to figure out laws which are not based on some mathematical element. I mean, so in a sense, it's unavoidable that out of the many topics, mathematic topics that our mind can provide and develop and very abstractly consider, a few of them must be around to help us understanding why things are happening always in the same way. Because if they were not, I just don't know. However, I mean, I would like to bring you about a specific case where mathematics is really making a tremendous help to us, which is quantum mechanics. Okay.
Mm-hmm.
I mean, that quantum mechanics today is the theory most tested, verified of all the theories. And there is nothing which escape the fundamental laws of quantum mechanics, in spite of the fact that when we think with our intuition, it is extremely hard, if not impossible, to really understand what is going on. So there, apparently, mathematics is really playing an extremely important role, or in a sense, our thinking does not match the mathematics which we are using. What do you think about that?
No, that's a very interesting point. And just to harp on my theme, I would say that, as you say, quantum mechanics is very much experimentally verified. And now we have these just fantastic experiments that people are doing with being able to create Schrödinger atoms and all kinds of stuff. And these quantum, it's just astonishing to me that people can do that. And in all cases, as you say, the mathematics works out and quantum mechanics tells us the right answer. My feeling is that the whole problem of trying to unify quantum mechanics and gravity is in some way tied up with the fact that we can't really understand what goes on with quantum mechanics. So, as you say, we understand the mathematics, we can work out the theories, we can calculate interactions and forces and so on and so forth. But if you ask somebody to explain what's really going on, I mean, there's the famous thing Richard Feynman said about, nobody understands quantum mechanics. You just have to figure out to do it. And that's all you can say, which is unsatisfactory, I think, if you're a physicist, because you would like to have a better idea of what's going on. And my feeling is that that gap in our understanding in some way is probably crucial to being able to find a unification between quantum mechanics and gravity. The thing about quantum mechanics I find most baffling is non-locality, this apparent effect in quantum mechanics that things happen everywhere at once, which is just completely contrary to what we understand of physics in general. Old-fashioned physics, a billiard ball hits another billiard ball and it goes on its way and everything's localized, there's an interaction and off it goes. But even when you think about a simple case like a photon interacting with an atom and raising an electron to a higher state, that interaction is not localized because it's a wave function somehow interacting with another wave function, and you can't say where exactly it happened. There's no particular location. It's just sort of an overlap between two wave functions. And according to the calculations, the wave function sort of changes everywhere at once. It goes from being this wave function to that wave function in an instantaneous way. And the mathematics captures that, but there's something very unsatisfactory about it. And of course, people over the years have tried to get around that. There was David Bohm with his hidden variable stuff, which I don't think works. And there are other people who try to do the same kind of thing. But general relativity, which is our theory of gravity, works in a very old-fashioned way. It's very definite. It's very localized. Things happen at particular places. So I think, to me, that's the most glaring mismatch between quantum mechanics and gravity, is this issue of non-locality. And maybe there's some better way to understand quantum mechanics that somehow gets around that. Or maybe it comes down to, space itself being quantized, time being quantized. But what does that mean exactly? I don't know. But that's, to me, a big gray area. And I think the fact that we rely on quantum mechanics to understand, that we rely on mathematics to understand quantum mechanics in the way you say, in a way, to me, that's a weakness. Obviously, it's an extremely successful theory. There's nothing wrong with it. But conceptually, it strikes me as kind of a gap in our understanding. And I hope that one day somebody will figure that out. But I certainly don't know the answer.
I don't know either, but in a sense, when I think to that, I spend a lot of time thinking to that, because I try to explain these kind of things to my younger colleagues or to the public. It's one of the most fascinating topics, of course. But I came to the conclusion that it is because we are not trained since in high school about the complex functions, and we are unable to see these properties. So it is about mathematics, but it's like you are using real numbers all the time, and then suddenly we stumble on something which is intrinsically complex, and the properties of those numbers are much more general and non-local than the properties of real numbers. But this is just an intuition. So I just don't know. It is marvelous, however, what this kind of mismatch, which works so beautifully between how we see things and how we use them. In one of your chapters, you talk about somebody which Kuhn mentioned about science, or analysis and comments that you basically think that today we are back to normal science. There is no our attention or to get excited about physics. Is that what you think?
I'm sorry, the audio was cutting out there. I couldn't get the question.
I will take away my video. Maybe it's better. Okay, so you in a part of your book you talk about Kuhn, which is talking about normal science versus revolutionary science. And I'm asking yourself, you think that nowadays we have too much normal science, and we are annoyed and bored because there is not enough revolutionary science? Is what you think?
That's interesting. I got to say, I remember reading Kuhn's book on scientific revolutions quite a long time ago, and I thought at the time I read it, I thought, oh, this is really interesting, very brilliant. But over the years, as I've learned more about the history of science, um, I think it's sort of a false distinction. I think people like Kuhn and other people writing in the mid 20th century about science and about physics in particular, they were very much influenced by two revolutions. You had the quantum revolution, you had general relativity, and these were two enormous transformations of the way we think about the physical world. And so a lot of what those people, Kuhn and his colleagues, other people at that time wrote about, was very heavily colored by the fact that they'd gone through this time of revolution. But to my mind, if you look back at the history of science overall, you can't really draw a clear distinction between revolution and normal science, because there's always, there are some kinds of science that are very incremental. You just measure something a little more precisely, or you extend a theory to some realm where it hadn't been operating before, you sort of creep your way along. And then other times things come along that are more transformative. I mean, an example would be Maxwell, James Clerk Maxwell, coming up with the unified theory of electricity and magnetism. That was a great leap forward. But was it a revolution? Well, I don't know, because the elements of what he saw and was able to put into mathematics already existed. So, Faraday, who I mentioned before, and Ørsted, and all kinds of other people, Ampere, had come up with theoretical ideas that were moving in that direction. And then Maxwell came along, and he was the one who put it all together. But I think historically, you can see Maxwell as being the culmination of quite a few years of progress. And it was certainly a significant moment when he published his first paper and said, here's the unified theory of electromagnetism. But it's not the kind of thing, for some reason, people talk about as a revolution. Whereas when it comes to quantum mechanics, people say, oh, a revolution. What I'm saying is, I think this idea that there's a spectrum. In other words, there's not like normal science and a gap and then revolutionary science. There's the most tiny incremental science at one end, there's the most transformative science at the other end. And I think you can find examples of everything in between that over the course of history. So to answer your question, if I can remember what it was now, we're living in an era where, if you like, normal science has been quite remarkable. So, the discovery of gravitational waves, which we talked about earlier, you could say that's an example of normal science. It's something that people have known about for a while, had been trying to figure out how to measure them, spent an enormous amount of time and effort coming up with ways to measure it, and eventually they did. And to my mind, you can say that the discovery of gravitational waves was, in its way, a revolutionary finding. But it was the culmination of a lot of normal science, just people doing, day after day, going one step forward, one step forward. So as I say, I think this whole idea of normal versus revolutionary is overstated. And I think, maybe we are in need of a revolution in terms of particle physics theory, because I sort of feel we've got stuck in a bit of a rut with superstrings. Like, people are working on superstrings almost to the exclusion of everything else. There are some people working on ideas outside of that. But it's questionable to me whether the effort and the manpower that has gone into that has really been rewarded with intellectual insight. And maybe we do need some sort of huge transformation. I would love to see that. And whether it'll happen in my lifetime, I just don't know at this point.
Okay, maybe I have a last question. Let me play now the cynical one in the room. It is about the growing role of data. I mean, the push towards digital twins of everything we could imagine to describe a complex system, including physical complex system. Mm-hmm. And on top of that, the increasing role of artificial intelligence. In my video, so there is a better sound. It is a fact that we are getting application of artificial intelligence more and more. We are making simulation of the reality more and more systematic, just because we cannot measure and observe everything. The question which I would like to ask to you is this direction have been about investigating nature with this kind of digital tools. Do you think will bring us any to find some new, really new, fundamentally new surprise, some revolutionary science or not? Let me ask more precisely. Once I was listening to a seminar, a talk by one of these people which are fans of artificial intelligence, which they believe that the artificial intelligent robot will take over our race and will define the future of humanity, not anymore like servant by leaders, okay? And I asked him, look, what about creativity? What about research? What about capability to invent new things? This is really something which cannot be imitated by artificial intelligence. And they said to me, no, we are working on that. We are studying the pattern of scientists so that we can implement it 20% better in our machines. So I think that if that will ever be true, then is the end of science and it becomes very, very, very boring. But I want to ask you this question. What do you think about that?
Well, yeah, that's a very big question. Just as a historical note, I wrote a book some years ago about the life of Ludwig Boltzmann. And one of the battles of his lifetime in science was the question of the existence of atoms, which for a while some people were skeptical about. And Ernst Mach, who was the Austrian physicist and became kind of a philosopher, he objected to the existence of atoms because he said we can't see them. You can't measure an atom, you can't see an atom, you can't sort of hold an atom between your fingertips and say here's an atom. Excuse me. So he said they're not real. We shouldn't theorize about them. And he came up with this philosophy that went through various incarnations later on. He said the only thing science should concern itself with is finding quantitative connections between measurable phenomena. And so to him, classical thermodynamics in its old form was perfectly fine because it didn't really matter that nobody could say exactly what entropy was, as long as it was this thing you could measure and put in equations, that was fine. And he had a few followers, but ultimately his philosophy was to my mind the negation of science, because it said you don't really want to know or even ask questions about what's happening or why it's happening. You just look at the phenomena and try to connect them together. And I mention that because, in a sense, that's what a lot of artificial intelligence right now is doing. I mean, one example would be, excuse me, Google Translate, which I use from time to time. You put in a piece of text in some language and you go to Google Translate and it coughs it up in another language. And it's not always great, but it's often pretty good, surprisingly good. But when you look at what Google Translate is doing, it's not actually translating in the sense that a human being would translate. A human being reads a text in a foreign language, understands what it means, and tries to convey that meaning in another language. Google Translate just goes all over the internet and the cloud and everything and says, oh, I've seen this phrase before and this is how it was translated. And there's that phrase and it was translated like this. And it just puts it all together. So there's no, if you like, there's no thinking involved as we would understand it. And yet it comes up with a pretty decent job quite a lot of the time. And I think artificial intelligence, when you apply it to science, I mean, suppose you just have some enormous amount of data from some experiment. And in a sense, in particle physics, people do this already. You do collisions at LHC, it produces just enormous amounts of data, and you have to use computer routines to get rid of a lot of it because it's just too much stuff. And you have to say, well, that's not interesting and this not interesting. And at the moment, it's human programmers who say, well, we'll throw out those kinds of results because we don't care. These kinds of results don't count. These are the ones we're looking for. You could envisage a future, I suppose, where an artificial intelligence machine of some sort would go through all the data and say, oh, here's something that might be interesting that you may have overlooked. But it would be doing it on the basis of some sort of anomaly in a, I don't know, statistical sense. But would it be science? Would it be thinking? You know, that gets into a difficult question. I mean, my own belief, and I have no, you know, this is just a belief. I can't explain why I think this way. I think the difference between artificial intelligence now and us with our brains up here is mostly a matter of scale. So even the biggest computer systems and the biggest networks still have a fraction of the computing power of what we have up here. And so even though they can do things that sort of look as if they're intelligent, they're not what we would call intelligent. But if that process goes on, and if computers continue to evolve, and if systems continue to evolve, then I don't think there will be suddenly a quantitative moment or where you make a leap from being not intelligent to intelligent as a computer. It will just be a gradual sort of ramping up. You know, I remember reading a long time ago, there was an old Arthur C. Clarke story along the lines that you were mentioning, where, you know, the human race evolves and creates science and builds computers and starts building computers that are so big that they sort of take over, and the computers go on to kind of be control the intelligence of the universe. And meanwhile, human beings are just left with this nice planet, and they retire and they play tennis or whatever, and they have a nice time. So that's the good side of it. The bad side of it is obviously, you know, Terminator and Skynet and all that kind of stuff, where the computers become malevolent. I think that's a long way off still, but I mean, it's not totally out of the question that something like that could happen. I don't know. I mean, but whether, you know, it's an interesting question whether at that point computers or artificial intelligence takes over all the thinking, all the creation of science and art and music, and we're just left to enjoy the products, or I don't know what would happen to us. We'd get bored, I guess. So yeah, it's an interesting question. I think honestly that's a long way away still, despite all the advantage, all the achievements and advances we've seen in our lifetime with computers. That's still a long way off, but it's not a future that's completely out of the question, I think.
So, I mean, I finally got from you a gleam of hope that there is still space for critical thinking, creativity in science, and maybe some new result in the coming future.
Yes.
Okay.
Thank you so much.
And
well, thank you.
It was a real pleasure to have this exchange with you.
Yes, I enjoyed it very much. Thank you.
Thank you so much for these interesting meetings. I loved to hear physicists talk about miracles too. Maybe our minds needs imagination and not only mathematical rules. I studied humanities, so I love the link between science and philosophy, art, literature. I love that.
Oh, well, imagination is definitely required.
Yeah.
Absolutely. Yeah.
Okay. I found out an unknown world. Thank you so much.
Okay.
Thanks to Planetario, Marica, Rosario, and la professoressa Misiano. I bring greetings from Gianfranco Bertone, the president of Scientific Committee of Cosmos. I want to remember the book Quale Universo, published by Giugno Einaudi Editore. The author, David Lindley, is here, and I hope to see you soon in Reggio Calabria. Thank you so much. And the next appointment is on Tuesday for another meeting. And thank you very much. Bye.
Thank you. Thank you.
Thank you. Bye-bye.
Bye.
Bye.
A posto chiuso?